Good morning. So, where were we? Last week and the week before, we talked about index compression. So after introducing the standard index, the standard inverted index, and we saw very big trying to construct an index when it doesn't fit on a single machine, we tried to find smarter solutions in order to deal with bigger collections. And I don't know if you heard of that quote. I don't have the name of who said that on the top of my mind, but you can Google for it. You should only be given several computers, more than one, if you already know how to use the first one. And knowing how to use the first one, in that case, means being able to compress the index in such a way that it fits on a single machine. And we saw two things that we can compress. The first one was compressing the dictionary. So we looked at a couple of techniques in order to compress the dictionary. So you probably remember that we dropped the B+3 and we replaced it with binary search, but binary search on something smaller. So we lose something in terms of speed, it's going to be slower, but we gain something in terms of space. So there is no free lunch. Whenever you want space, you need to pay with time. And then we looked into how to compress the postings lists. And for this, we looked at the bit level, how to encode sequences of integers. So I have a couple of questions in order to reactivate the knowledge that we introduced last time. So I'm going to just fire them at you. First, you probably remember that one of the encodings was called the thermometer code for a very good reason, it has to be said. So which one of these is the thermometer code? Is it the gamma code? Is it the variable byte encoding? Is it the unary code? Or is it the front coding? Seems like we need a bit of time to wake up today, but I'll wait a little bit more for that first question. 11. Does anybody need more time? Can you raise your hand, please, if you need more time? Okay, I'll wait. Was that you? 12? Okay, awesome. Okay. Okay. I'll only check that so you can still enter an answer. Yes, you got it right. The unary code. Why is it called the thermometer code? What does it look like? Yes?
It gets longer the longer the code, or the longer the number gets.
Exactly. It's exactly like a thermometer. So not the thermometers that you probably know today, but the good old ones with mercury, where the temperature is directly proportional to the length of the mercury. So the unary code behaves exactly the same. You have exactly as many ones as the integer you're encoding, and then you put a 0 in order to end it. Is that a prefix code? Who thinks it's a prefix code? Who thinks it's not a prefix code? Very good. Yes, it is a prefix code. Why? Because you know when you have the 0, you know where it stops. So it's a prefix code. Okay. And the others, they exist, but they are not called thermometer code. The gamma code, remember, the gamma code uses the unary code. So the gamma code starts, it looks like a thermometer on the left, but it's not a thermometer on the right. So this is why unary code is the correct answer. Okay. Let me try, since we are at the unary codes. This is a tricky one, but I want to see if you can figure that out. So I told you something about optimality. So I told you that the gamma encoding it has a certain length. I got criticism in the lecture, very good one, that it's twice as long as a normal encoding, so why don't we just use an integer encoding? So there was criticism on the size that it takes, because it looks like a waste to have twice the length. But it's absolutely not. And I talked to you about the entropy, and I told you, so the entropy is like the size that you would need in order to encode something in average. And I told you that the gamma code is just within a factor of 3 of the optimal size, and even a factor of 2 if you allow for a little constant, a little one. So I told you the gamma code is optimal, and it has a very nice property, is that it is optimal regardless of how the integers are distributed. This is an amazing result. Regardless of how the integers distribute, if it's skewed, if it's more uniform, and so on, it's optimal. I think it's not a secret to you that the unary code looks less optimal than the gamma code. And there is something that may surprise you, is that, oh, well, actually, I should not tell you, because I'm actually already excluding an answer, so who knows, maybe, you know, in every case. So for which one of the following probability distributions on integers is, believe it or not, the unary encoding optimal in terms of length? Is it never optimal? Is it always optimal? Is it a Poisson distribution with lambda equals 1? Is it a binomial distribution, or is it a distribution with negative powers of 2, which you know sums up to 1 because you're computer scientists and you know everything about powers of 2? Who needs more time? Okay, let me show you the answer. Aha, interesting. I got you with the Poisson distribution. I completely made that up. So it is the negative powers of 2. Two of you got it right. I can even give you the intuition very quickly. I'm not going to do a formal proof, but just the intuition of that. Because actually, it's hard to find. I mean, if I don't tell you anything, it's very hard to come up with that one. But if I tell you about that distribution, you can very easily see that it actually makes sense. Because remember that we are summing over minus p of x log of p of x. And this, if this is 2 to the power, so I could put n in there because these are integers. I have some distribution, and now I'm telling you this is 2 to the power of minus n. So the log is then minus n, and there's a minus again. So I'm taking the log in base 2 here. It's just simpler. So you see, just so you know, don't worry about starting with 0, with 1. We kind of set that, so I'm just, for simplicity, just 2 to the power of minus n. Probably you want to exclude 0, maybe also 1, or if you have 1, you divide by 2, but that's not the issue. What I'm telling you is that if you apply the entropy formula, you get a sum over 2 to the power of minus n times n. And what's interesting is that if on the other side you compute the expected length of the thermometer encoding, then what is the expected length? It is the sum of the probabilities times the length. And what do you get? The probability, it's time to 2 to the power of minus n. And what is the length? It's n. So you see that it matches. And this is the reason why it's actually optimal for this very probability distribution. So of course, this probability distribution is extremely skewed, because if you start, for example, with 1, half of the numbers will be 1s, and 1/4 will be 2s, 1/8 will be 3s, and so on and so on. So it's very, very biased to very short numbers. So you see it makes sense that the unary distribution then is optimal. So you can see that if you know that the gaps in your postings list in some strange world in which the gaps distribute that way in collections, then you could actually directly use the unary encoding instead of the gamma encoding. But in real life, of course, that doesn't exist, so this is why we use the gamma encoding. Okay, so this is a mathematical curiosity that the unary code, even though it looks very unoptimal, it is optimal for one of the distributions. So this was one. Then what do we have here? Another one of gamma codes. I would like you to answer this one as quickly as possible. Meaning, I don't want you to think too much because you don't actually have to decode them. So, can you spot which ones of the following are valid gamma codes and which ones are not? So, normally I activated several answers possible. If you correctly remember what I did last time, I even had a tool with me. You should very easily spot them. Yes?
You cannot select multiple.
Oh, you cannot? Oh, sorry about that. Maybe I can close it again. I need to... I will just take 1 minute in order to do that. So can I maybe close and reset? Reset, yes. Okay, and then several answers possible. Oh, that's not the right one. Yes. Can we see it now? Yes. Now you should be able to select several answers. So I gave you 6 of them. Again, don't think too much. Try to think on a high level. What's interesting is that pedagogically, the ability to answer this question is directly correlated to the ability of decode the gamma codes. Because if you're able to quickly answer this question, then you understood the general principle behind gamma codes. So I have 15 answers, so let's... Yes, exactly. So 0 is the encoding of 1, that I've told you. 100 is the encoding of 2. Then we have this one here. So how you can tell that this is a gamma code, because if you measure the length here, you have 4 ones, and that means you must have 4 bits here as well. Here you have 5 of them, and you have 5 of them here. Happens to be just ones, it's a coincidence. So this is fine. This 0 here should always be in the middle, the 0 that separates. Why is this one not a gamma code? Simply because here you have 3 ones, but here you have only 2 bits after the 0. So it's not a valid, yes?
But why is the lowest one on the gamma code?
I'm coming to that. So I would have, in the exam, I would have made more precisions, of course, because if some of you argue with the right arguments, I can accept this as a valid answer. The idea is that in reality, when you store the gamma codes on disk, you always store them on actual bytes, right? So you will have extra zeros at the beginning. Here, I am one level of abstraction higher that I'm not on hardware, and technically, if I have to decode that as a gamma code sequence, this would be a 1, this would be a 1, and this would be a 3. So that would be the sequence encoding of 1, 1, 3, but... Oh, okay, I see, you could argue that way. So was your argument that this is a gamma code because it encodes 3 integers? Okay, then I can accept that. Because then I could make the question more precise, saying which one of the following are valid gamma codes for 1 single integer. So yeah, you can argue with the words. Then I agree with that. Okay, but it means that you understood what a gamma code is, and that's very good, so perfect. Okay, I have another one that is now connecting it back to the notion of encoding, because we use the gamma code in order to encode postings lists, after all. So can you try to encode these postings list? These are the document IDs, 1, 3, 5, 50, 52, 500. Try to encode that. I'm not telling you anything. You know, you have everything we did last week. You know how to encode that. Notice that I'm saying postings list. A posting is a pair of term documents, but as I told you, the term is implicitly at the start of the line, so we don't repeat it. So 1, 3, 5, 50, 52, 500. You don't, of course, it's a multiple choice, so you don't have to actually encode it completely, but you can probably deduce the answer. So the last two I grouped in sequences of 8 bits for convenience. You probably guessed by now that it's enough to look at the first 8 bits in order to select the correct answer. Who needs more time? Can you raise your hands if you need more time? Anybody? Okay, so let me show the answer. You can still answer. It's just live results. Yes, I'm very happy about that because now you got this right. You remember the gaps? You need to compute the gaps. So you encode the first one, but then what you encode is the gap between 1 and 3, which is 2, and then between 3 and 5 is 2 again, 50, and so on. So this is why this is the encoding of 1. 100 is the encoding of 2. 101 is the encoding of. Oh, what did I do here? I think I had something. Yeah, anyway, you understood that we are encoding the gaps between them. Pretend you didn't see that. Once you encode the gaps, you use the gamma code. So the gamma codes that are the first two in there, and these are variable byte encodings. You remember? The 0 is in order to tell you it's the last flag. So this is a variable byte encoding right here of the sequence. Just pretend here that the difference between 3 and 5 is 3, which I don't know what went over my mind when I did that, but anyway. So this is a variable byte encoding on 8 bits, and these are gamma codes. And in this answer, I didn't take the gaps. I took the actual numbers in this answer, sorry. And here I did exactly the same thing. Okay, so if you accept that 3 plus 3 equals 5, then I think you all accept that the first answer is valid. Don't worry, because in the exams, there's plenty of people that proofread everything and solve it, so this should not happen in an exam. Here I'm just alone, so when I deal with a lot of zeros and ones, then that happens. So let's end it and continue a bit on the lecture. And jump directly over to where we were, which is at the very end, actually. We were almost done. Variable byte encoding, there was the gamma code. Here. This is the one slide to understand the gamma code, by the way. And here you can see that this is all repaired compared to last time. You can see that here you have the length of 2, so you have 2 ones here, and then it's correctly encoding with 2 ones and then 2 bits. Here you have triple ones and then 3 bits here. Here you have 4 times 1 and then 4 bits there and so on. So this slide is fixed and will be re-uploaded or was already re-uploaded. I told you about these things in the questions. I told you it's a prefix encoding because you know where it stops, and I told you it's a universal encoding because it's optimal regardless of the distribution, the gamma codes. Then I showed you the entropy to show you that. Okay, so here is this last bit that I wanted to do, which is something that is done in the book, but I wanted to give you more details and a visual about what is done in the book. How much can we compress the inverted index? So you know that the compression depends on how many postings we have in each term and how they distribute. So imagine that I'm sorting, hypothetically, we don't actually do that, or at least not yet, but maybe in a couple of weeks. Imagine that I'm sorting my terms in my standard inverted index, and I start with the most frequent term, and then the second most frequent term, and so on and so on. That means that the more I go down, the less document IDs there will be for each term, right? And the way it distributes is actually given by a law that is called Zipf's law, which, if Swiss German is your mother tongue, is probably easier to pronounce than I do. And then this is a hyperbole, meaning that the first time is extremely frequent here, and then it goes down and down and down. So if we use that formula here, k is some constant divided by the rank, so it's 1 over x. It's 1 divided by the rank. So if we use that now in order to compute the size, first we need to renormalize things. We love to renormalize things whenever we add things. So instead of k, I'm using c, and I'm doing that in such a way that it sums to 1. So I'm just dividing by some constant factor in such a way that we have basically a curve of which the integral is 1. So that gives us, if you look at the number of occurrences per document that a term appears, is the document length times c divided by the rank. So it's the document length multiplied by the some occurrence frequency. So which gives us L times C divided by the rank. I'm just calling the document length L. And now if I'm using that in the standard inverted index, I'm assuming I have all of my terms here, all over there, then the number of postings that is in any one given term here is the total number of documents times the number of occurrences in each document. Because this is the overall number. You remember it's the total number of documents in the collection. This here gives us the proportion of them in that collection that contain the term, right? And this is what decreases with Zipf's law over time. So we have always that constant here times something that diminishes according to the Zipf's law. So now the number of documents is n, so now I add this little n on the left, and NLC divided by the rank gives us, when we go here, it gives us the size of each posting, and rank is 1, 2, 3, so the only thing that changes is rank, right? All of this is constant. So we have something that is like a hyperbole in there. If you look at the shape of the standard inverted index, it would be like a hyperbole. But now we want to sum over that to compute the size. And the way we are going to that, there is a little trick. We actually group mentally the terms in blocks, and the blocks take a size of LC, it's a constant, terms. So each block has LC terms. Here I'm taking 3 as an example. And if we have these blocks, then the first block has LC, so the rank of the last one is LC, then the rank of the end of the second block is 2LC, and so on. Right? Who is following? Okay, so I have these blocks here, and now I'm going to try in each block to approximate the size of the posting, assuming that within a block they all have the same size, and I'm going to take the size of the last one. So I'm going to pretend that the size of these 3 postings list is the same as this one here. Why? Because the rank here makes it very easy to compute the formula. So I'm approximating that the size of each posting here is constant within each block, but each block will be smaller than the former one. Okay? So if I do that, it's just primary school math, because if you compute, if you take here NLC divided by the rank, but then the rank is LC, you see that LC disappears. It cancels out. And what I'm left is n. Each one of these terms here has approximately n postings. So the third one, actually, this one here has exactly n postings, and this we approximate of having n. Then I go down, so rank is now 2LC, so it's half, because we divide by a number twice as large, and then n times 3 postings per term, and so on and so on. Right? Who's following? Okay. So again, just to remind you of what we are doing, this is an approximation. I'm assuming that they all have within a block the size of the last one, and what I have here is the size of the last one, because I just plug in this number here into this formula and get this, primary school math. Okay, so now what happens? We have n divided by something that I call j, n divided by j equals 1, j equals 2, j equals 3. So now I'm coming to this actual posting list where I have n divided by j. So can somebody tell me, if I have n documents in total, what is the average size of a gap here? Approximately, if it's like uniformly distributed, if we approximate. What is the size of a gap? For example, imagine that I have, in total, I have 1,000 documents, and my posting list has 500 of them. What will be a gap, roughly? Two, right? It's just the division. Because if they are uniformly distributed, they're basically, so 500 over 1,000, it's, for example, all the even numbers, 2, 4, 6, and so on, that gives you a gap of 2. So if you assume that there's n documents in total, and there's n divided by j postings, which we calculated from the previous slide, then we get a gap of j in average, right? So n divided by n over j gives us j. So we have a gap of j that I'm just putting here. So here it means that if we have n postings out of n documents, the gaps are gaps of 1, right? We have them all, basically. Here we have, for example, all the even documents. Here we have every multiple of 3. Doc ID, it's just approximations, okay? But now you remember that based on the size of an integer, you know that the size, so the size of an integer in binary form, what is the size of the gamma code of this integer? Approximately, yes? Yes, it's approximately twice. So if I get one example, this is just one example where I use j instead of the actual numbers, then this is what I plug here. Here, I have 2 times log j plus 1. So it's I need to take the log, right? But it's twice the size. So this is where the twice is. So this is the length of the encoding of one gap right here. And I multiply it with n over j, because n over j is the number of gaps. So this is the size of one gap, and this is the number of gaps that gives us the total size of a posting, right? So one of these here, 1/3, one posting list, will have that many bits, approximately, right? So now I have this. How do I get the total size of the block right here? I multiply with LC, right? It's the size of a block. So now I multiply this with LC to get the size of the block. That's what I did here. And then we sum over there, and this is what we get. This is the total size of the index, of the postings in the index. And I remove the 1 just in order it's a constant. So this is what I get. So why am I doing this? First, because we do want to know how good we are compressing things. So we need to compute the approximate size of the posting lists. And if we can compute this, then we can compare it to the uncompressed postings list, the uncompressed index, and that tells us how good we do. The other reason is pedagogical, because maybe you didn't, who understood the calculation here? Some of you who didn't? Okay, so if you didn't, I recommend reading the book and doing it offline, because if you understand what's going on here, it's a validation that you understood how the index is compressed, that you understood how the gamma code is built, and that you understood seed flow. So this here is merging plenty of concepts we saw in the lecture, so I really recommend taking the time to understand what's going on right here. Okay? And by the way, the next exercise sheet will be about heap flow and zip flow. So it's a very good opportunity for you to test them on a real data set. because, it seems arbitrary that in Heap's law, it behaves in the square root, so the terms go in the square root of the size of the tokens. Heap's law is a hyperbole. It's pretty amazing to have this kind of patterns in reality, because this is real data. It's people writing articles, people writing books. And if you look at large scales, you see that it behaves like this with the square root curve and the hyperbole. But we are going in the exercises to put it to a little stretch, because we are actually going to use the Shakespeare corpus. And I think maybe, I don't know if you look forward to it, but it's pretty amazing when you look at Shakespeare. You would think maybe it's going to shake a little bit the Zipf's law, or the Heap's law. So I'm not telling you anything, you will discover it. What happens if you try it with Shakespeare? Will it still resist the reality? So how did we do? So the whole point of computing the size of the compressed index is to see how we do. So this is all taken from the book. So in the book, the uncompressed version of the hypothetical use case, which was Reuters RCV1, I think, the uncompressed index. So the uncompressed index is if you're very naive and you store every document ID on 32 bits, or 64 if you have more than 4 billion documents. 400 megabytes. So what happens if we compress? So we can store it uncompressed on 20 bits. It was our first attempt when we tried to just cut and pad the terms on 20 characters. Then we had the variable byte encoding, which is when we try to encode the gaps of the postings list with the variable byte encoding, the one with the zeros and ones that flag the end. We are already at almost 1/4 of the size. That's pretty good, right? And then if we use the gamma encoding, the Elias gamma encoding is just to give the credits to Peter Elias, who is the author of the encoding. So the gamma encoding, we are at 100 megabytes. We do even better than the variable byte encoding. It shouldn't surprise you because the gamma encoding is kind of an extreme version of the variable byte encoding. So the variable byte encoding is still grouping bits in packets, in bytes, but the gamma encoding is doing it bitwise, that you're even to compress the encoding of 1 to just 1 bit, which is 0, okay? So this is how we did. So you see that it's, of course, it's not 10 times shorter, so it's not like a miracle, but still, you can see that if the index is compressed to 1/4 of its size, you can reverse the arguments and realize that you can store a collection 4 times as large on the same machine, right? So we are doing pretty good here. Okay, so this is, and the size of the collection was 960 megabytes. So you can see, maybe you thought, how much space can an index take? Certainly much less than the actual input, right? But this is actually not true. You can see that the size of the inverted index here is half of the collection. So, an index can be pretty big. Just because it's an index doesn't mean that it's much smaller than the collection. So the credits, of course, of this for this week are chapter 5 of the book. You probably realize, right? Every week is one chapter of the book. I will tell you, so right now it's very linear, but I will skip a few chapters because I'm avoiding the machine learning part. But I will tell you every time. So read chapter 5 of the book, okay? Let me throw a few more questions at you. So, can you catch an encoding sequence that is both the gamma code and the unary code? Does it never happen? Does it always happen that they can be interpreted as both? Is there only one, or is there a couple of them, but not always? Very quickly, it's a very, very easy one, if you think a little bit. It's the kind of question that validates that you understood, basically, because you can only understand this question if you really understood the codes. Yes? What is this one sequence? Can somebody tell me? Yes? The sequence?
I think it's 100. Not sure.
100 is not a unary code. Look for a smaller one. 10 is not a gamma code. Even simpler, yes? Just 0, because 0 in gamma code is the encoding of 1, and in the thermometer code it's the encoding of 0, because you don't have any 1. Okay? Great. So this is good. And then that's a wrap-up of the lecture of part 6 before I move to the ranked retrieval 1. So I showed you plenty of compression schemes: gamma coding, front coding, variable byte encoding, and block storage. Which one encodes which? So which one encodes posting lists and which ones encodes dictionaries? So go ahead and pick the right answers. Eight, 9, You know what happened in one of the previous lectures? I actually said that I was calibrating the exam based on the questions that I'm asking, and suddenly the number of wrong answers just skyrocketed for some reason. Okay, 10. So what do we have? Yes, you got this right. So posting lists, it's gamma coding and variable byte encoding, and dictionaries is front coding, you know, with the, when there are several times words beginning with the same prefix, we just write it once, and block storage of dictionaries as well. Very good. So let's wrap this up and move to the next part. I'm going to start it still before the break. So we are again in the advanced part of the lecture. We've started compressing the index, but everything we've been doing was more or less the same paradigm of retrieval. What kind of queries did we process? Boolean queries, exactly. And this is new. This is totally new. This is totally different. We are going to look into something completely different than Boolean queries. So indeed, this is the kind of queries that we answered. So what's the idea? We have a couple of documents. We have a query, a Boolean query, and, not, or. We have some very simple grammar here. And what we get out of this query is some output, which is a subset of documents that match the query. So we've looked into everything. We've looked into how to build an index, how to, out of the index, compute the results of the query, that's very binary, isn't it? Either a document belongs to the output or it doesn't belong to the output. But today, this is what we are going to do. We are not going to look into Boolean queries anymore. So no more and, no more or, no more not. We look more into Google-like queries. One of the reasons is that you don't get billions of people using your search engine if you force them to use Boolean queries. This is not how the world works. In the world, people prefer to query using this kind of queries where you just put some words into Google. Who actually uses Google with Boolean queries? Whoever did a query on Google with and or not? Some of you, interesting. So, of course, Google is a very advanced system, so they are kind of hybrid, doing a little bit of everything. But most people use Google that way. They just put some words in there, and then comes some output. But you probably noticed that in Google, Google doesn't throw at you hundreds or thousands or millions of documents, right? It only outputs the first 10. And then if you want the next, you can click, but it only outputs the first 10. So you understand that if you have a Boolean search system and there's a billion answers, this is totally useless to you because you have no idea where to start with. You have no idea which ones of the documents are useful to you. And what's worse, with the Boolean system, you also very often get empty results because your query was formulated in a way that no document strictly matches your Boolean query. So you see that with the Boolean querying system, we are the two extremes, no results at all or two large result sets. So we need this new paradigm that outputs the documents in a ranked way, meaning that there is some kind of score that gets computed, which tells you the relevance of a document, and then you compute, you sort them by score, and you output the first n. This should remind you in SQL of the limit and offset keywords, because this is more or less the same thing that we are doing here. So we are switching to this new paradigm, and you will realize that this is actually very interesting. It's completely different from what we've been doing with Boolean retrieval. We are going to use a lot of linear algebra. But what's interesting is that there are things in common because the overall structure of the index is still identical. So if you have the standard inverted index in mind, you will realize it's not so different from what we did before. But the similarity kind of stops here. But instead of directly throwing at you the linear algebra of ranked retrieval, we are going to take it step by step and take a step back from the kind of searches that we can do. So imagine that you are in a library. Maybe the good old times of a library 20 years ago, 30 years ago. When you would go to the, back then, in the good old times, you would go to some library. They did not have a full text search system over all the books of the library implemented. That was just too much effort. Maybe some had, but it took a lot of money to implement. So how do you think that we searched for books back then? With a computer. Anybody? I'll just directly tell you. You will see it's actually obvious. Yeah, this is where I'm going. This is just a reminder of what we've been doing, that we abstract the document as a list of words, and then as a set of words, and then we have this vector of Booleans. But this is what I'm coming to. If you look at the books into a library or on Amazon or wherever, you will see that until now we only opened the books and looked at its full text. But if you look on the page of the book, there's extra information there. There's title, authors, hardcover, publisher information, the language, the ISBN number, the dimensions of the book. I don't know if people buy their books according to their sizes, but you could also technically do that. The shipping weight, maybe you have constraints on the weight, the customer review, and so on and so on. So you see that we don't have just the free text of the book. We also have all of this metadata. And people actually use that. Like on Amazon, you actually search through the metadata. So instead of the Boolean query, what you used already 30 years ago, 40 years ago in a library was that you had some kind of software that provided you with a few fields here, title, author, and so on and so on. And what you would do is enter your query in there. You would enter a title that you're looking for, you would enter some authors and whatever you want, and you leave the rest empty. And then the system would search for the books, but it would search for the books with their metadata, not with their actual content. So if you actually think of that, what's happening is that the metadata is very structured. You know, I told you at the start of the lecture we are dealing with unstructured data, which is just a bunch of text. But if you look at the metadata, you can actually store it as a relational table. You have the title, the author, the publication date, the language, the country, the price. You have all of this metadata. If you're well organizing your library, you have all of this metadata in a table. So what that means concretely is very simple. This is actually a classical database problem. If you want to retrieve some books with this title, this author, and so on. So here I actually don't have much to teach you about that because you've already covered that with the information systems class on SQL, right? So who would very easily be capable of implementing this? I guess all of you, right? So this is what I'm coming to. But this is a good way to start because we can actually push that a little bit. But I'm going to do that right after the break because I see it's 10 a.m. here. So I'll see you at 10:15 in order to continue on this. And I will slowly bring you to the ranked retrieval model with that. Welcome back. So we were in the middle of looking at ranked retrieval, where the goal is to sort results by decreasing relevance. And I told you that in older times where we didn't have the luxury to index the full text of the books, we had to use fields like title, author, publication date, and so on, which is a classical database problem. Can somebody tell me very quickly, in a classical database, how do we speed up the such queries? If I give you an exact value for a title, publication date, and so on, and I have a very large table, what do I use? Yes? Yes, more specifically, two kinds of indices. It's exactly the same ones that we've actually been using in the standard inverted index. So these are hash tables, exactly. So hash tables, they are very good in order to look some exact value up, like a string or a date or something. B trees and B plus trees, they have an extra feature. They are capable of doing range queries. So if I have a B plus tree, I can also do queries like give me all the books published between 1990 and 2000, for example. This I cannot do with a hash table except for enumerating the years. Okay, so we have these two classical search structures that you probably are familiar with from this and other lectures. So the idea is very simple. Now we are going to have some indices associated with the parameters. Sometimes we can even have indices that mix compound keys and so on, but this is the idea. So for the title and author, for example, we could have a hash table. For the publication dates, which supports ranges, we could have a B plus tree. Then language, countries, and costs, which also is an integer. Maybe a B plus tree makes sense. Right? So this is how we could solve the problem. It's a classical database problem. And then, of course, after that, once we have the structures, we have the posting lists. Right? Because in the end, we want to search the documents that match this. So when I'm saying posting lists, let's say that I'm pushing the interpretation of what a relational database returns in order to use information retrieval technology. But if you think of it, what you are returning with these indices are rows, and a row is a posting or is a document ID. So I'm abusing the terminology here just in order to show you how, in the end, what you end up with is a list of documents that you return as results. And then you intersect results in pretty much the same way. Okay? So the new big picture is that we have some parametric indices that use these field queries when you enter your search terms in boxes. And maybe you still want, on top of that, to do a full text search. You know, mix the two. So you can say the author that you want, and then for this author, you can find the terms. And this is the standard inverted index. But here, of course, the posting lists are associated with terms, right? Here it's associated with the entries in the indices, like all the books written in some year are on the same row and so on. Who understands this? Very good. But this doesn't quite get us to ranked retrieval. So what can we do? We can do zone search. Because right now, I'm assuming you type the exact value of the title you want or the exact author that you want. But as you may guess, this is not practicable because you cannot know always the exact title. So what you would like to have is some kind of full text search, but within title and author, for example. So you would like to have a mini version of what we've been doing for the full text, but for the title of the books and the abstract. So what you have then is, instead of having all of these field and parametric indices as classical database indices and the terms of the full text separate, instead, you have some maybe parametric indices. Maybe you keep the price, language, publication dates. I don't think that a full text search makes any sense there. But for the title and the author of the book, you may want some kind of full text search, right? And if you use, I'm sure almost all of you already use the ETH library website, right? And when you use that, you expect a full text search on the title and author. at least. I'm not sure I remember if the ETH library has a full text, has the full text of the books, but if they don't, then Google has that. Google has this service where they actually index the content of some books. So now we can just take a quick look, but you will not have a big surprise in there in the way it's done. What I'm telling you is that we can actually mix them and merge them into a single index. Instead of having separate standard inverted indices, we can mix them in the same. So how do we do that? This is the good old index that you know, with the terms on the right and the postings on the terms on the left and the postings on the right. So what we do is I'm just making a bit of room here, so we have more space. And what we do is we append the where that is. So that dot body means that it's a term contained in a body. So we abuse the space used for the term in order to say in which zone it is. That's called the zone, title, abstract, body. The body is the actual content of the book. And then if we mix that, then we are going to have for each term one posting list for ETH appearing in the body, and these are all the documents for which ETH appears in the body. And then we have ETH.title, which is a separate term, and then we have all the documents where ETH appears in the title. So we have a bit more terms. It's basically the Cartesian product of the term space and of the zone space. Who understands this? Who doesn't? Okay, I'm assuming you do. And this is the alternate way, because you can also turn that upside down, and instead of encoding the zone in the term, you can instead keep the exact same old term and encode the zone instead in the postings. So for example, here, for ETH, you could store it together with the document ID where it appears. So for example, ETH appears in the title of document 1, in the abstract of document 2. You can mix the two. For example, here you have Zurich that appears in both the title and the abstract of document 3. This is an alternate implementation. Both are good. Both make sense. So either you store the zone in the term here, or you store the zone in the postings, as you wish. Okay? And of course, this is compatible with compression, because you could, so of course, if you have this, you can just treat them as terms. Like pretend that .body, .title is part of the term, and ignore, you pretend you don't know that it's actually a zone index. And in here, if you encode the zones, there are not so many of them usually. You can encode them with integers and find some scheme similar to gamma codes in order to encode that. For example, you can have a gap expressed as a gamma code and then 2 bits. And you know it's always 2 bits in order to encode the zones, for example. Okay, but how do we get scores out of that? We have these zones. Somebody is searching for keywords in the title, in the abstract, in the body, and somebody inputs some search query with some words. Could somebody very quickly guess how we get a score out of that? Which documents may rank higher than others, depending on the zones, the query terms? Can anybody guess? Imagine that I have a query, let's say ETH, and I have a couple of candidate documents that I found in my index, the standard inverted index, modified with zones. And I'm telling you some of the documents have ETH in the title, some others have them in the abstract, some others have them in the body, some of them have it both in the title and abstract, some other of them have it everywhere, title, abstract, body. Can somebody tell me how you would rank them? Yes?
I would say there are 2 kind of rankings. One is like title, abstract, body, which is like title is probably more important because that's the thing I can remember. And the second thing is like how often does it, or where does it occur? So if it occurs in title, abstract, and body, it's probably more relevant than if it only does occur in either of them.
Yes, exactly. So there's 2 things that you said. First, it's more relevant if it appears in several zones. It's called the zone, this thing. So it's more relevant if it appears in several zones. And maybe it's also more relevant between 2 zones if it's in the title compared to the body, for example. You are absolutely correct, and that's exactly the essence of what I'm going to show you. So here's how we make a score out of that in order to reach these results of returning the documents that contains the words in as many zones as possible, and even better if it's the title and the abstract. So suppose that I have this query like single term for now, and I have the keyword information, the word information, and I have these postings right here in my index. I'm using method 2, so the zones are encoding in the postings. And now I'm going to implement what you said, giving weights to the zone. So I is some zone, and L is the total number of zones. So here we have just 3, body, title, abstract. And GI, so there's G title, G body, and G abstract. There are the weights that we want to put, right? Can be equal weights. You can give more weights on one side or another. These are the weights. These are the zone weights. For example, I could take 0.5 for the title, 0.3 for the abstract, and 0.2 for the body. Okay? If they sum up to 1, that's perfect. And then, what do I use for SI? What do you think we use? We are computing the score of one document for one term here. What do you think we can use to multiply GI with? Anybody? Plain and simple? Just the 0 or 1, right? A 1 if it belongs to the zone, and a 0 if it doesn't. So in essence, what this complicated formula is doing, it's just adding the weights for the zones in which the term appears. This is what it does. This is just a mathematical formulation of that, but this is what it does. And if I'm preparing for later here, you may recognize some kind of scalar product in there. And that's not a coincidence, because we are actually going to come to that later. So this is the more compact. It's amazing how in the history of math and physics, we are capable of compressing formulas, because this is formula compression, right? And scientists have been doing that for ages. I think one of the most recent ones is the Hamiltonian. Like, you have this super complicated quantum physics formula with plenty of complicated things, and one day somebody just wrote it with some kind of h and square and so on, and then you have the formula compressed in just a couple of things. So this is the compressed version, and of course, the more you are capable of understanding compressed formulas, the better it is. Right? So this is why being formal is extremely useful, because this is also easier to learn. Because if you learn this complicated formula, you need to remember everything. But here, all you need to know is scalar product. Scalar product, then you know that formula. It takes less space in your brain. So concretely, what we are doing is that we have these weights here, and I took exactly the ones I told you, so 0.5, 3, and 2. So here, for some obscure reason, I put a higher weight on the body. Maybe it doesn't make sense, maybe it does, but we can take any weights we want. So now, let's look at this one. So information occurs in the body of document 1. So what we do is we add this weight, there's only one of it, and we get that. And this is actually the scalar product of G with S for this document. So we are doing the scalar product of this vector here, 0.325, with the vector 0, 0, 1. 0, 0, 1. It's basically the zones in which it appears. And that, what we get is 0.5. Then let's do it with this, title and body. So we add the title weight and the body weight, 0.8. And then for the third one, the same thing with body and abstract. So we add the two weights, and 0.7. When we put it all together, we have computed for all 3 documents, 1, 4, and 5 for each posting. We have a score. What do? We sort that with some, of course, maybe not bubble sorts, but an efficient sorting algorithm, and then we get the result with document 4 that you can see has the highest rank for a good reason. It appears in several zones, and it appears in the body, which has the highest weight. So you see that there are several reasons, but that leads to the highest score. Who understands this? Right? So that's it. We have a new paradigm. We switched over from Boolean retrieval, where it's a yes-no answer, to ranked retrieval, where we are sorting the documents using scores. And for the score, we are using the weights of the zones. Okay, so by zone. So you can see that using the zones gives us ranked retrieval. So then you can generalize that if you have several terms like information and retrieval, then you look at 2 entries in the index, and then retrieval is in title and abstract for document 4, so it's this plus, title plus abstract is 0.5. Information is in title and body, so it's 0.3 plus 0.5. So what you do then, and this is an important step, if you have several terms in the query, information and retrieval, what you do is you add these vectors. You add the scores here. So what you have for the title zone, you have a score of 0.6, 0.2 for the abstract, and 0.5 for the body. And then you add all that, and you get 1.3 as the total score for document 4 for the query information retrieval. Okay? I only generalize that to 2 terms instead of just 1. Okay? So you see it's a bit more involved than what we did. How did we do it in the Boolean query for implementing several terms? What did we do? If I give you the standard inverted index, do you remember? We computed the, yes? The intersection of the posting lists. Exactly. We computed the intersection. That was very simple. It's a first-year bachelor lecture. So here, it's slightly more involved because you see that instead of just noticing that 4 and 4 is in both and returning 4, we do a bit more work here. We compute scores and arrive to a total and so on. So it's more paperwork than just the intersection, but that's the cost of ranked retrieval. So yes, we use the intersection in the Boolean querying, and here instead of just intersecting, we also do an additional thing. We also accumulate the scores here on the fly. So we don't just notice that 4 is in both, we actually accumulate the scores. Right? And there's a slight difference is that you notice that here 3 is here, but not here. But we will still return 3. But we will just use the score from here, and here it's the score of 0. So you see, we are no longer doing just the intersection. We are really accumulating the scores. And I will come back to this accumulation thing a lot. You will even have an exercise on that. So now, a short parenthesis. I told you about the weights of the zones. I told you that you can assign title, abstract, body, or many others. You assign weights. But how do you pick the weights? That's a very important question. You want to pick the weights in the way that it's useful, that it returns relevant results. Remember, precision, recall, it's all these things. So you want to find the right weights. So the way you do that is that you have, imagine that I give you a data set with plenty of queries, documents, and so on, and their relevance. So here, these are query results. S1 is the occurrences of some terms in some documents, and R1 is just a flag that tells you, yes, it is relevant to me, or no, it is not relevant to me. So again, this vector here in the data set, one single entry in the data set, the vector is just S. It's a vector of Boolean that tells you which zones contain the term, any hypothetical term. And on the right, associated with these Boolean results, I have a 1 if it's relevant or 0 if it's not. And that was done by humans. Maybe you hired a few people and gave them all of these queries, and you asked all of these people, please flag each one of these queries if, yes, it is relevant or not, it is not relevant. Okay? And you did that for plenty of combinations of terms and documents. Okay? So once we have that, we can compute with this magical formula that I gave you with the scalar product. Of course, you need an open mind here because I'm adding an extra index here, which is for the instance of the data set that we have. So I have one more index here compared to earlier, but you see that we are still summing over the zones here. So we are doing this computation. In an ideal world, in an absolutely perfect world, this would give me a result of 1 if it is relevant and 0 if it's not. If I found these magical weights that give me exactly the relevant documents as opposed to those that are not relevant. So what you do is you compute the error, which is the difference between the two. And the smaller it is, the better it is. Right? Who's visiting the machine learning lecture? So I guess you're not learning anything in there, and for good reason. So what you end up doing is that, remember that the goal of that is to find the weights. We are trying to find the weights in such a way that when we compute this gives us, ideally, 1 if it's relevant and 0 if it's not, and we would like this to be the same result as we have in our data set. So in other words, we are computing the argmin of this, and this is machine learning. And this is why I'm stopping here, and we will not actually go into how we do this. This is machine learning, this is outside of the scope, but here what I'm doing is I'm connecting information retrieval to machine learning, right? And this is really two disciplines that go hand in hand, because you have a lot of machine learning in there. So who of you visiting the machine learning lecture, without me telling you anything, would be capable of implementing this? If I give you the data set with J and R, S and R and so on. Who would be capable? Very good. Very good. And if you're not visiting the machine learning lecture, do not worry. I'm not going to ask you anything, just understand the high-level picture. But the fact that you're capable now of using material of 2 different lectures is really, really good. And just for the sake, because in the book they actually explain this, sometimes you don't even need to actually train and use stochastic gradient descent or that kind of things, because here you have a direct formula in some cases. But enough said about that. I'm leaving that to the machine learning scope, just informing you that the way that we actually compute the weights can be done with machine learning. So, now coming back to the abstraction that we have, until now, we have always simplified the documents as a set of words. This is something we've been doing since the very beginning. But now we are going to switch, we are going to do something, we are going to switch to bags of words. Meaning there's 2 things that we completely threw away with the set of words. We are throwing away the order of the words in the document. And the second thing we were throwing away is the number of occurrences in the document. Why did we do that? Because it was Boolean retrieval. So who cares if a term appears 1,000 times in the documents or once, because all we want is to know whether or not it is in the document. But now we would like to improve this system beyond zones, so without having to use these zones that we've been doing now. And the way to do that, it's actually very intuitive. If all we have is this set of documents and we only consider one zone, like the body, if I notice that a word is appearing 1,000 times in a document and it's appearing just once in another document, then maybe the document that has it 1,000 times is more relevant. So maybe that document in which the terms appear 1,000 times should have a higher score, right? So we are still doing this scoring and ranking, but now we are going to take it to the next level without field search, without zone search, just with the full text version of the book. And for that, we need to go from a set of words to bag of words, because we need the information of the number of occurrences. Who is following this? Very good. So here's what we need. I need to define a couple of terms here that are extremely important for you to remember, because everything will be based on that. Imagine that I have a document that I call DE, and it has a couple of terms. I just have 3 different ones here, foo-bar and foo-bar. So how can we compute something interesting in there? Well, that's what we call the term frequency. Out of these documents, one single document, not the entire collection, just one document, for each word, its distinct term. Here, I can compute the number of occurrences, so you can notice that foo appears 3 times, 1, 2, 3. Bar appears twice, here and here, and foo-bar appears twice, here and here. Again, this is also something you probably saw in the machine learning lecture. I think I saw some slides on that. It's exactly the same idea of having the number of occurrences here in some documents. But the way we are going to use that will be very specific to information retrieval. Because actually in machine learning, what you can do is use that actually as training sets. These are features, right? So this is the way that the machine learning people see that. I will not see that as features. I will see that as something different that we will see, but this is a shared representation. So we can use the term frequencies. So who thinks that this is a good score? It gives us an indication, right? If I have foo 3 times in a document, and in another document it's 10 times, then it will rank higher. Maybe we could directly use that as a score, the term frequency, right? So my question is, why is that not a good idea? That would be a very naive idea. We just use, for a score, given a term query, a search query with a term, we use this as the score the number of times the term is in each document. And then we ranked higher the documents that contain the terms more often, and we generalize that to several terms just by adding the scores, right? So why is that not a good idea, this naive approach? Oh, I should start it. Sorry. So the first answer is because ranked retrieval, if we do that, used as a term frequency, then actually it comes down to Boolean retrieval. So we are just doing exactly the same thing as before, because the whole linear algebra will be completely useless compared to plain intersections of posting lists. That's the reason. Or no, maybe that's not the reason. Maybe the reason is some terms may be concentrated in just a few documents, which is problematic. Maybe it's a different reason. Maybe it's because the most relevant documents have low term frequencies and we did inverted term frequency instead in order to rank higher the documents that have less occurrences of the term. Or maybe, you know, maybe it's not true. Maybe it's a great idea. So three answers so far. So again, to emphasize and say again, term frequency it's a quantity, a number, an integer, indexed on two things, on a term and a document. If I give you a term and a document, a pair of term documents, there is a term frequency. You need both. So this is why on the slide it's always indexed with the term and the document. It's very important to understand because the other quantities that I will give you will not necessarily be indexed on the same thing. So that's very important. We have one term frequency for each pair of term document, aka a posting, a non-positional posting. Let me see what you answered. Very good. You actually, the majority is right here. That's very good. Yes, this is the reason. This is exactly the reason. All the rest is just made up and doesn't make any sense. So here's why it doesn't work. Here's an example. I'm using the term frequency as a score, hypothetically. I have two documents A and B, and these are the occurrences. These are the term frequencies. It shouldn't be surprising to you that we have a two-dimensional matrix because I told you the term frequency is indexed on the term and the documents. So it's indexed on the Cartesian product of the term document space. So foo occurs 5 times in A, once in B, and so on. So if we use that as scores, then all we need to do for each document is sum that up, and we get a score. So document A will have a score of 7. Document B will have a score of 5. Why is that not good? Why is that not a good scoring scheme? Can you see that here? So the issue here, why we may think it's a bit annoying, is that bar here, this term here, never ever occurs in document A, but it occurs in document B. It means that bar may be some very specific or knowledge-specific term that occurs in very few documents. So maybe if somebody is inputting this query foo bar and foo bar, he would like document B, not document A, because document A doesn't even contain bar. Right? So here, you see it's not perfect. If we're using this scoring scheme, it incorrectly ranks A higher. When I'm saying incorrectly, I don't mean in absolute incorrectly, but incorrectly in the sense as we don't really want that. The users do not expect that. A user would like B to be ranked higher. So how do we do that in order to account for it? We need to quantify how rare a term is. What's the best way to quantify how rare a term is? We just count how many times it occurs, maybe in the entire collection. So let's take a collection. Here I have 3 documents. I'm using the bag of words semantics. This is why I dropped the order here, but it's bags. It's bags because we repeat the terms here. Bag of words. So 3 documents, and let's say it's my entire collection. So if I compute the frequencies, you will find out that in the entire collection, foo occurs 4 times. 1, 2, 3, and 4. And none here. So this is 4 here. This is called the collection frequency. Collection frequency is only indexed on the term, not on the document. Right? So for each term, we have one collection frequency, not for each term in documents. So only T is my index for that. So 4, 5, and 5. And then maybe we can use this as a quantifier of rarity, but there is still an issue with that. There is still an issue with that because you can see that foo bar only appears in the document here. So foo bar is technically very rare, but still, here you would have the impression, just looking at that foo is more rare, is rarer than foo bar. So you see that something's not quite right in there. We didn't catch the fact that foo bar is rare because it only appears in a single document right there. So instead, we use the document frequency. It means that we map all these documents here to the terms, And instead of counting the total number of occurrences of the term in the entire collection, we use the number of documents that contain the term. Okay, so that's how it works. So foo is contained, you see two arrows, two incoming arrows, it contains here and here, that gives us 2. Bar is in 3 documents, all 3 of them, and foo bar is only in that document. This is the document frequency. Okay, so we have term frequency, document frequency, and collection frequency. Okay? But maybe there is one more thing that we need to, do I have it here? No, I didn't have a question on that. So there is one more thing we need to do, because the document frequency, if it's higher, then the document should be less relevant, because it means that the term is not rare at all, right? So there is one more thing we need to do. We need to inverse it, right? We need it to be higher if the term is rarer. So we take the inverse. And the way we do that is we divide 3, it's the total number of documents, divided by this, and we take the log also. We just take the log to keep our sanity and not having it explode. So if I take the log of the total number of documents divided by this, I get this score, and we get exactly what we want. We get here. Yes, we get the highest score for foo bar, and that's great because it's the rarest. We got exactly what we wanted. We get the highest scores for the rarest terms. This is called the inverse document frequency, also called IDF. Now we can put it together. We can put it together because we have the term frequencies. Again, it's 2-dimensional here because for each term in document we have a number. Then we have the inverse document frequency with this magical formula log of n over x. And we have them here. Here it's 1-dimensional. We have this IDF for each term, but not for each document. So how do we do that? We just combine them. We just combine them in what is called the TF-IDF. And the TF-IDF, not very surprisingly, is just the product of the two. So we multiply everything here by 5, everything here by 10, and everything here by 3, and we get this table. Who's following? Perfect. That's called the TF-IDF. Remember that, because the TF-IDF is the score that we are looking for, right? So all we need to do now that we have the TF-IDFs of, let's say I have this query here, the same one as before, foo bar, and 2 documents. Computing the score, again, we are adding all of these things. It's the scalar product G scalar S, right? We are adding all of these things. So here we have 25 plus 6 is 31. I was better at doing the math in here. And here we have 5 plus 30 plus 40 plus 3 is 48. Bingo. We have exactly what we wanted. Now, B is higher ranked than A. Why? Because we accounted for the fact with the IDF there that foo bar is rarer. Okay? So we have a score. This is perfect. What did we do here? I didn't pronounce the word too much, but we are actually using vector spaces. This is what we are doing here. So since we are doing vector spaces, we may as well embrace it and just use linear algebra terminology that you're already familiar with. So again, model of abstraction, we always need a level of abstraction. We started with documents that are lists of words. We abstracted them initially as sets of words, dropping the order and the number of occurrences. That gave us this mathematical abstraction as a vector with zeros and ones. That was the S vector that we had originally. Okay? Now, I'm using the bag of words because we want to consider how many occurrences there are. And with the bag of words, we can have term frequencies. With the set of words, we can't. Because with the set of words, it would be 1 everywhere. But now we have the bag, so we can have actual frequencies. And we can represent a document as a vector of numbers. What numbers do I have here? I just arrange to have the TF-IDFs. Okay? I'm going to consider the TF-IDF for every term within that document. Okay? TF-IDF is for every document and term, every pair of document term. So that gives me a vector of documents. So again, this is the set of words setting. In the set of word setting, it's only zeros and ones. So what happens if you only have 0 and 1s in a vector space? What you are in the end doing is you are at the vertices of a hypercube. You know, if you look in 3D, you consider vectors that only have 0 and 1s in their coordinate. What you get is just the cube, the vertices of the cube. Okay? But now, bag of words, I don't have zeros and ones anymore. I have any numbers in there. So I have a vector, it's more generic. It's a vector here in R to the power of the number of words, M, the power of the number of terms. So here, what we put in there, for now, let's pretend it's TF-IDFs, but just so you know, we could have the term frequency. I just told you it's a very bad idea, very, very, very bad idea to have the term frequency. TF-IDF initially, or we can also use other weighting schemes, and this I will show you how other weighting schemes we have. It's very easy to understand. It's like a restaurant menu when you can pick options. Let's pretend it's the TF-IDF for now. So what do we get? The documents are vectors, so we can use this graphical representation of a vector space. Where will these vectors be? Anywhere in my vector space? Will I have document here or here? Anybody wake up? Yes? Exactly. It's going to be right here because the numbers must be positive, so it's in the first quadrant, right here. So that's it. We have documents, they are vectors, and they are all in the alpha quadrant. Sorry, the first quadrant, thinking too much of Star Trek in here. So it's in the first quadrants, D1, D2, D4, D5, D3. I'm asking you to have a bit of imagination because right now I have 2 dimensions. So basically this is when there's only 2 terms. It's a very simplified model. I'm projecting on a plane. You need a bit of imagination and imagine that in fact we may have thousands or millions of dimensions, right? But it's finite. Don't worry, it's finite. You could argue, no, it's infinite because the terms could be anything, but in fact you always have a collection. So the number of terms is finite. So we have a finite vector space. R to the power of the number of terms, which the book uses M for. Okay, so we have this quadrant. And the documents are vectors. This is the abstraction that we have with the documents. And so we can note them like that using vectors. In the following slides, I'm using the arrow across it. But what I mean is the vector of the documents that contains the terms, and it starts with M. So now, we need a norm. We need, because we have a vector space, we may as well use that. So not just any vector space, but it has some structure. So who remembers the Euclidean norm for the linear algebra? Very good. So the Euclidean norm is given by this magical incantation that sums the squares of the coordinates and takes the square roots. It's also known as the norm 2. You can also have the norm 1, which is with the absolute values, the norm 0, the norm infinite. But we take the Euclidean norm because it has very nice properties, and in particular, it's compatible with scalar products and all these things. So this is why we like to use this norm. It's very, very popular. So of course, since you were in the linear algebra lecture, you are capable of knowing that this is what you have in your mind because you already know what that is, and this is already saved from the previous lectures in your brain. So this is just the Euclidean norm. So what we need to do here is some renormalization. So whenever we have a document with the occurrences and so on, it may be anywhere in that quadrant, but we would like to renormalize things. We love to renormalize things. I already did it with in the first hour with the ranks and tips law. We love to renormalize things, so we would like it to bring it back here. How do I renormalize a vector? The answer should be instant, right? You went to linear algebra. How do I renormalize a vector? Yes? Exactly. So I want the unit length, so I divide by the Euclidean norm, and there I am on the unit sphere. So the unit sphere is all the vectors that are of distance of 1. So it's the unit sphere in the first quadrant, of course, just this quadrant. Very good. So this is the formula. And concretely, so what you get in practice is you have this row vector non-normalized, and you just need to divide by the norm and get the normalized version. Okay? Then, Well, pretend you didn't see that. And just tell me. Well, let's make it quick because I know you saw it. So tell me, how would you compare two documents? How would you say that two documents are similar? And I'm saying documents, but I don't actually mean that I'm giving you the books. I'm directly giving to you the vector representations. So how do you tell if they are similar or not? I left out renormalization in there, of course. So imagine that everything is normalized. We divide it by the Euclidean norm. 9 answers. It's pretty cool what we can do with linear algebra. So we could compute the outer product of the vectors and take the determinant because it's a matrix. We could compute the inner product of the vector but take the inverse or not, which is the first answer. So should we invert it? Should we not invert it? You need to think similarity as opposed to distance. Or do we take the cross product? Remember, the cross product is here, it's 0, and when you open, then it starts to be higher, and the norm of that. So what should we use to measure the similarity of two documents? And the answer is, because you saw the slides, but I'm sure that you would answer that correctly if you hadn't seen the slides, the inner product of the vectors, and this is the correct answer, because if you measure the angle here, that's actually what it does. If you do the scalar product, you're actually multiplying with the scalar product the two vectors. Here I'm not using the normalization, but this is in order to tell you that this is not so nice, because imagine that you have two documents on the same line here. You could argue that they are very similar. Imagine you take one document and just copy-paste it 1,000 times. What it will do is just make the vector longer, push it there, but it's still the same relevance for your search. So this is the reason why, in practice, you do the scalar product, the inner product, on the renormalized version. And surprise, surprise, what you get is the cosine of the angle, theta. So since you visited the linear algebra lecture in your first years of bachelor, this is very easy to remember because all you need to remember is it's the scalar product of the renormalized vectors. And the vectors, they contain the TF-IDFs. It's that simple. So we spent some time on that, but I hope that now, at the abstract level, you understand what's going on, right? It's very, very mathematical. So now, of course, we will need to do some computations on that. So this is a good quantification of similitudes. I'm insisting it's the similitudes. If it's similar, it's higher. If it's dissimilar, it's lower. So these are very similar documents. These are very different documents. Yes?
Is there a difference between similitude and similarity?
I didn't push it that far. Similitude in the sense of a transformation called the similitudes? Or how do you mean?
Just as the words.
Just as a word. I'm not making any difference. I just mean they're similar. But yes, I'm sure that you could also go deeper and argue about which one, but I'm not. I'm using them in the same way, right? So the similarity, if you prefer to use similarity, just similarity. But now, let's push it, and this is the cliffhanger for next week, because now you will see that everything adds up. How do we treat queries? How do we treat queries in this model? And this should be an aha moment, because the queries, they also contain words, and they are not Boolean queries. They are just bags of words. In general, sets of words. I don't know if people input several times the same words in the query, but the idea is very simple. A query is just like a document. It's just a vector as well, just maybe just with zeros and ones, but this is it. So now that we have the queries, es liegt auf der Hand. Also it's very easy, because you can see that if you use this idea of similarity or similarity, you compute the scalar product or the inner product in there, and you see that this is a very good result for that query. They are very similar. This is a very good result, so D1 and D2 for that query. So all we need to do to get the ranked retrieval is just compute that. We have the query, we have the documents, we need to compute it. This is what we are going to do next week. So just, as usual, to end, to check whether you followed, I'm just working under the assumption that since you know everything about linear algebra, you should have all the toolbox to understand what went on today. Very good. This is actually perfect. It's exactly, oh, wow, okay. So talk to each other. If anything you don't understand, you can send us emails. You can also talk to each other. It's a very good exercise. If you try to explain to somebody else, it's a very good exercise for you to be rock solid in your knowledge, because it forces you to push it to a way you can explain. And just saying that helped to push everybody to the 80% bucket. Okay, so this week the exercise is on Heap's law and Zipf's law. It is not a week that will contribute to the bonus points, so you have less pressure. You already had 2 weeks so far. Am I correct that this week doesn't count? So there was week 3, week 5. Week 5 was the gamma codes that counted. It was the second one. And then next week we'll count again on the vector space model in linear algebra. So this week should be a bit less stressful for you. And then for the rest of the semester, again, less stressful, because then the bonus points will be decided. Okay, so enjoy the exercise session. If you do not understand anything, drop us an email to me, to the TAs. Do not hesitate and talk to each other. Okay, so have a nice exercise session.